efendim? 2 tahtayı, evet.
Solutions are online. What's in the homepage? Okay, let's start. Do you guys have any questions before we begin? Anything from previous weeks? Oh, you can ask whenever you like. So last time we were back to this problem. We had a box, and each side of this box was the length of L, and two terminals connected. We haven't drawn these yet, but we will have them eventually. And then we said we have electrons inside, and these are free electrons. So no collisions, nothing. There is free electrons, no interaction between the electrons. We completely ignore the lattice. So, but the only difference is that we are going to treat these as quantum electrons. And these electrons are confined within this box. So what we did is we solved the Schrödinger's equation. If you just do it for one dimensions, you will see that the solutions will have this form. The way I have written this was something like this, and I said this lambda n is 2L over n, where n is this integer that comes from quantization. And the overall wave function needs to have three such indices, and L corresponding to three different states. Mistakenly, I have written them as a summation last time, but this is actually an multiplication, so 2 pi L in the z direction. So the overall wave function will be represented by something like this. But rather than the wave function itself, we are more interested in the energy values. So I'm interested in these energies. Again, I'll have three indices, and simply the energy is going to be summation of these indices divided by, since we have equal sides, okay, so there's multiplication of this thing. Okay. All right. Now, so far this is quite straightforward, but this time I'm not just interested in a single electron within this box. I'm interested in n electrons. Okay, so I have this many electrons. And I'll treat them as isolated electrons. They don't interact with anything. So this is in general called the single electron picture. Although I have many electrons, they don't interact with each other. So this is, of course, a significant simplification compared to electrons interacting with each other, which would overly complicate. Indeed, it becomes impossible to solve the Schrödinger's equation analytically for even 3 electrons interacting with each other. So we made this assumption. Let's have the simplest possible solution so that we can understand the very basics of the concepts. Now, if you remember last time, I took this one-dimensional square law, and we have these energy values, okay, and they go up. Now, if I have n electrons to fill up these states, how would I go filling them up? The idea here is that electrons are spin 1/2 particles, and due to this spin property, they cannot occupy the same quantum state. Now, if you don't know what spin is, then I strongly recommend you to refer to the textbook or search it online. Spin is an intrinsic property of all the elementary particles, just like mass or charge. Spin is built into these elementary objects, like electron and quarks and all the elementary particles. They carry a spin. Okay? And this spin can take very different values. It can be 0, it can be 1/2, it can be 1, it can be 3/2, and so on. So you can have lots of different spin values for particles. And based on the spin value being integer or half integer, the statistical behavior, as we'll see in a moment, varies significantly. For the case of integer spins, we call them bosons. For the case of half integer spins, we call them fermions. This comes from a guy named Bose, and this is named after Fermi. And in the case of fermions, what we have is these particles cannot occupy the same quantum state, which means that if we go back to this example, let's say I have a spin-up electron. Since I have spin 1/2, I can have 2 states, spin 1/2, spin up and spin down. You can say spin positive, spin negative. There's a risk of confusing with the chart. You can say spin A, spin B, it doesn't matter. Classically, we refer to them as spin up and spin down because of this experiment. Again, I'm not going to go into the details, but this proves that the spin, quantum spin, is quantized. So this is a very nice experiment. If you're interested, you can check. But if you trust me, or if you already know what it is, then this spin up particle being in this E1 state represents a single quantum state. So the overall wave function, if you want to write it, is going to be composed of the spin part of the wave function and the position part of the wave function. So it represents a single state. So the next electron, if I were to, let's say I enforce a spin-up electron to be here, cannot occupy this state. It needs to go to this higher state. But I can form a different state with a spin-down electron, so it can go here. Now, if I had, for instance, a delta particle rather than electron, then I would be able to fill up many states here. I would have 5 different states. So I could have more states, but we are dealing with electrons and we are dealing with solid state physics, so we rarely are interested in anything else. So this is the only configuration that I make. Now I already have another spin up in the first excited state. Then the next thing I can place is a downspin electron. So this spin configuration plays a critical role in how I fill up the energy states in this box. Okay. So if I have these n electrons, and if I were to fill up all these states, then what I'm going to get is, let's focus on this 1D case. Each state is going to be able to take 2 electrons. So the total number of the maximum, if you like, energy is going to be n/2. Simply, for this one-dimensional case, this is what I'm going to have. So this guy has a special name, denoted with F. And that N also has this F. So the energy of that state is going to be simply 2N L squared. This is called the Fermi energy. And this is called the, well, this is not called anything, but this denotes the state of the Fermi energy. Okay. So this is just a definition, but as we'll see in a moment, this definition can be generalized to actually whole solid state physics. It's not only confined to this one-dimensional box, and it actually is a very useful concept in determining the properties, electronic properties of materials, because it in a way defines the energy of the highest occupied state. And that energy will become extremely useful when we start dealing with more complicated solids. Now, let me do one more thing. So, let me define this Kx, and it will become clear why I use this notation. So, my Kx needs to be 2 pi over lambda n, and you can see that this is going to be n divided by 2 pi over L. Again, I can here. Well, it doesn't matter. I have an extra 2 somewhere. I can get rid of this one, I guess, and it won't hurt since I have already 2 pi there. So let's stick with this one. Okay? So now, then I can write this expression. I'm just going to play around with the way I write that energy expression. So my EF can be written simply as h bar squared over 2m k f squared. Okay? Now, kf here is obviously defined as nf 2 pi over L. So I'm just playing around with the definitions. And this is sometimes referred as
the Fermi wave vector. Okay. Now we can switch back to 3D. Let's get rid of this stuff. So I can write down my k vectors as sum of these three. Okay. And simply at the highest occupied level, which corresponds to, let's say, N, M, and L, then this will become Kf, so that this definition will still be true. So you can generalize it to 3 dimensions very easily. Now, what am I looking at here? Let's draw this. Actually, it needs to be in 3 dimensions, but it's very difficult to draw a sphere in 3 dimensions. So let's assume we have a 3-dimensional space. Now, this k vector actually rotates on the surface of a sphere. Okay? So for any k values you take, or you're limited by this boundary. Okay? So you have a maximum value for your distribution for maximum occupation states N, and L. So this vector that defines the surface is actually the wave vector at the Fermi energy. Now, why is this so important? If you look at the sphere, you will see that this is filled up with individual states, okay, individual quantum levels that spans entirely the spherical volume. And this is another way to look at this problem of electrons' motion. If I say, for instance, my electrons move at a certain velocity v, now I'm switching back to a semi-classical picture, and let's say they move in x direction at certain velocity v, so you will see that this whole sphere will shift by a certain amount in the x direction, because now you shift, in a way, whole momentum values. It gains an extra momentum. So if you think about it, we can write this momentum as h bar k. So if there is a change in the velocity, which means it's a change in the momentum, then it translates to a change in the k space. That's why we actually insisted on going from reciprocal real space to reciprocal space, which makes things easier to a certain extent to analyze. I mean, here it may seem trivial. I mean, we have a box and there's an electron. We could perfectly solve it using a semi-classical approach. But imagine more complicated solids, where this Fermi energy will not be a perfect sphere, but it's going to be a much more complicated shape. It's going to be anisotropic. So this approach actually allows us to visualize such changes in a simpler way. Now, there are more concepts that I'm going to introduce here. I'll come back to this Fermi sphere in a moment. But let's do this. Now, the sphere has a volume of 4 pi kf cubed divided by 3, right? So its radius is kf, so kf cubed over 3 pi gives the volume. And what I'm interested in is finding the total number of electrons so it should be n. And I know that each state within this sphere is separated by this value, 2 pi over L, since it's a uniform distribution. So what I can do is 2 pi over L cubed, since it's in 3 dimensions. And I know that I can put 2 electrons per each state, per each k value. Thus, this expression should give me the total number of electrons. Okay? Now I can write an expression for kf, because I can sort of know the number of electrons within this box. It is going to be 3 pi squared n over v, 1 over 3. And here v is L cubed. This is the real volume of the box we have. Now I have an expression for kf. And I can make a relation between EF, number of electrons, and volume of my object. So I can write down my EF in a more user-friendly way. Okay, so V divided by 2/3. Okay. I have slightly departed from this abstraction. Rather than dealing with these k values, I have real values that I can measure, okay, for this Fermi energy. Okay, now let me get rid of these stuff. So again, it's going to seem like I'm going around the loop, but let me write down an expression for n in terms of EF divided by h bar squared 3/2. Now, how about this? I'm interested in finding the density of states, okay, which gives me the number of electrons that I can put per energy value. Okay, so number of electrons per energy. Now all I have to do is this. So my dE is going to be something like this. And 2 pi squared 2m h bar squared 3/2 e 1/2. Okay. Now what am I looking at here? The whole stuff that I was trying to do here is to sort of disconnect from this very abstract notation or notion of quantum mechanics and switch to a more understandable way of things. So if I plot, let's say this is the energy and this is the density of states, then all I have to know is that it will scale with square root of the energy values. Okay? So let's say I have a Fermi level of EF here, then I know that all of these states will be filled and the rest will be empty. So in a way, I'm looking at, let's say I have a completely empty box and I want to fill it in with electrons, then this density of states in a sense gives me a measure of the electron energies that I can put inside and how many electrons I can fit in an interval of energies. Okay? So it scales with square root of E. It's very straightforward to repeat the same exercise for this. This is obviously for a three-dimensional object. I mean, we assumed three-dimensional box. But it's very straightforward to extend it to a two-dimensional surface, a one-dimensional wire, and even a zero-dimensional object. And perhaps I can assign that as an homework to figure out these. By the way, there's an homework. I sent an email yesterday. It's due next Tuesday. Try to turn it in class. Okay? Any questions so far? It will become much more clear why we are going all through these in a moment, because at the moment we are dealing with a really trivial case. It's just a box filled with electrons. But if you remember the case where we applied the Koenig-Penny model, now in that model we had energy gaps rather than continuous energy states. And these concepts will become very clear when we start discussing them, but I have to introduce it in its simplest possible form. Any questions? Okay. Now, there's one more concept that I have to introduce before going into the properties of materials. That is statistical distribution of particles. Now, if you have noticed, there is no temperature in any of the things that we have done so far. We are dealing with objects sort of like they are at 0 Kelvin. We don't have any temperature expression that goes into any of our formula. So to be able to introduce temperature, we need to look at the statistical behavior of the particles, because now we are not dealing with a single electron, because in the case of a single electron, talking about temperature is rather nonsense, because, I mean, yes, perhaps you can define it. I mean, it's the average kinetic energy, but still, rather than talking about a temperature, you can easily talk about the average kinetic energy. So how can we introduce temperature into our equations? Now, what you need to do is look at how statistically these particles will be distributed for given temperatures. I'm not going to go into the details, but there are a few things that I'd like you to know. There are 3 types of distributions that you may encounter. One of them is Maxwell-Boltzmann distribution. So this case applies to more or less classical particles. And the idea here is this. I have n distinguishable particles, and they're free to occupy any energy state they like. So the counting, if I take these n electrons and I look at all the possible combinations, then what I'll get for the energy distribution, or probability of finding a particle at energy E, is going to be something like this. minus EF minus E divided by KBT. Now here, this is the Boltzmann constant. And this is the temperature. Okay. This is the Fermi energy. I mean, strictly speaking, it should be something called chemical potential, but it really doesn't matter in the case of solid state physics. Let's name it as the Fermi energy. Okay. So what I'm going to have, let's draw a sample distribution. Let's say this is energy E, and this is the Fe function. Then let's define let's say I have a certain value of Fe, and the distribution is going to look something like this. This is at one temperature. Then I can have another distribution, perhaps like this, for a different Fermi energy. I can have a different distribution like this. So, in a way, the distribution tells me that the values are going to be accumulated at certain levels. By the way, this needs to be, I'm sorry, like this. Okay? But the problem here is that it assumes indistinguishable particles that can occupy the same state. But this is not the case with the quantum mechanics, so we need to figure out statistics for both fermions and bosons. And for fermions, we have the Fermi-Dirac statistics, or distribution, if you like. And this time, the distribution function takes a form like this. So you have 1 over e to the e minus ef, again with a minus sign, divided by kBt plus 1. So again, I don't want to go into the derivation of these distribution functions, but it stems from the counting. Now, if you remember, when we fill these quantum states, we said, okay, I take this electron, I put it in this level, I take the other electron, I put it in that level. But the correct counting must be made taking into these two account. First of all, these quantum objects are not distinguishable. You cannot separate one electron from the another. There's no way to do it, or non-distinguishable. And then they cannot occupy same quantum state. So if you do the distribution, then this is the expression that you end up with. Okay. Then finally, I mean, we are not going to encounter with this one too much, but it's just general knowledge. Bose-Einstein distribution. Then in this case, the distribution is going to look like this, e to the minus, this the other way around, e minus ef divided by kBt minus 1. Okay? Now, if you look at this guy, These are the energies. This is the Fe. This function looks like this. At 0 Kelvin, it is like a step function. Okay, so this is 1. Let's say this is 0.5. This is 0. So this is the case for 0 Kelvin. So if you take the limit of T that goes to 0, you can see that below EF it's 1, above EF that becomes 0. Then as you increase the temperature, this function starts spreading out. I couldn't draw it nicely, but you can find it on the web page, better drawings. So perhaps I should draw something at lower temperatures. So as you increase the temperature, so temperature increases as you go down that way, the function starts spreading out. And perhaps, it doesn't have to start from 1, by the way. It can go down. Perhaps at high enough temperatures, you may end up with, of course, this is an exaggeration. Probably it won't happen. But you may end up with a much smoother function. Okay? And this point, the point where it crosses EF, always have this probability. It's 1/2 probability. Okay? And for the Bose-Einstein distribution, I guess it will be something like, most of the particles will be accumulated at lower energies because they can. Okay? They can occupy this same lowest energy level. So at finite temperature, there will be a small spread, but they can be accumulated at the lowest possible state. So we'll focus on Fermi-Dirac statistics for now, and there will be cases where we have, where we can switch back to Maxwell-Boltzmann distribution, because at sufficiently high temperatures, you can show that these become very similar or under certain conditions. Now, what happens to the distribution of my particles when I start increasing the temperature from 0 Kelvin? That's the question. I'm interested in finding the, let's say, number of, or density of electrons, not density of states, but density of electrons at a certain energy. So how should I approach to this problem? Well, I know the density of states. I know how these electrons will be distributed statistically for given energies. So what I can do is I can do this integration, okay, over the product of these two, over a certain range of energies. And rather than evaluating the integral, actually we can see how these density of states will be filled by just simply guessing from the distribution. Now I'm going to draw the distribution function over here. So this denotes, the black denotes the distribution probability. So let's say I have a distribution profile like this. What this tells me is this. At these energies, approximately from this on, probability of occupying these states is 1. So with certainty, my electrons will occupy these states. But as I approach to the Fermi energy, that probability starts decreasing. So what I'm going to end up with is not like this. This is the 0 Kelvin case, because if you consider, let me use the blue pen now, my distribution will come, continue like this in 0 Kelvin, and then make the step function, and then continue like that. So this corresponds to this red case. I would definitely have electrons here at 0 Kelvin. But now, I don't have that 100% probability of occupation. What I'm going to end up with is a slight curving down in these filled states. Okay, so there will be available density of states corresponding to these energies, and then it will start going down. But there is also finite probability of occupying above the Fermi level, above the Fermi energy. So my filling of density of states will look like something like this rather than the red curve behind, or red filled area behind. Now, again, this is a very significant result, because now I can see how my electrons behave at elevated temperatures. Now, I'm not confined to 0 Kelvin anymore. I can tell the maximum energy electrons in my system. I can see how they are going to be distributed, how they are going to occupy the energy states in my box. And when we extend this to semiconductors, for instance, or metals, we'll see that this approach is capable of explaining many of the phenomena that we observe in the insulators or metals or semiconductors and so on. Any questions so far?
From this curve, I can understand that in 0 Kelvin, there is no possibility that an electron occupy a level higher than a thermal level. But when the temperature rises, there is possibility.
Yes, exactly. So if you have n electrons at 0 Kelvin, when we start filling up these states, you will fill it up to the Fermi energy, which is sort of defined already by the number of electrons that you have. So you cannot have any electrons that are excited enough to jump to the next level, next energy level. It's a way to look at it. Okay? So we filled it up, and then we cranked up the temperature, and we started finding electrons at higher energies, because there's a probability of, and the probability distribution spreads. Okay? Any other questions? One more? No? Okay. All right, now, again, if you feel like you're missing certain details, please refer to textbooks or read them from online sources, because I don't want to turn this course into an introduction to solid-state physics. There are many exciting stuff coming up. This will just lay the foundations for them. So I'm just trying to introduce the important and necessary concept. And if you feel there's a gap, then I strongly suggest you to go and read these details. But these are, I'm trying to show you the bare minimum. Now, Let me see. Sure.
For the integration, you use the Fermi distribution.
Yes.
Why not the other one?
Now we are dealing with electrons, okay? So they are fermions and they have to obey Fermi Dirac statistics. And we are treating them as quantum particles. Now, again, under sufficient conditions, I could switch to Maxwell-Boltzmann distribution, but we haven't reached that sufficient condition here. It needs to be either too high temperatures or these electrons needs to lose their quantumness so that I can use Maxwell-Boltzmann statistics. I think for the Bose-Einstein case, we have to change our initial assumptions because we built this whole thing based on the assumption that we are dealing with electrons. So to be able to use Bose-Einstein distribution, then I have to we have to reconstruct everything from scratch, because the way they fill the energy levels are going to be different, the wave functions are going to be different, and so on. All right, now what's that?
10 minutes break.
We have 5 minutes.
Okay.
Yep. So now let's look at our insulators. What we have done so far was sort of a description of a metal, but now let's try to see how we can have a semiconductor or insulator within the framework of what we have seen so far. This is my K, this is the E. Let's say it goes from 0 to pi over A. And let's say I have something like this. So I have an energy gap here. Okay, so these are allowed states. Again, allowed. And this part here is forbidden. Just like as we have seen in the Koenig-Penny model. So a gap opens up. There are available energy states for certain momentum values. Now, there are certain rules. These are perhaps generalizations under the scheme of the single electron picture. Okay, so this is strictly applicable to single electron picture and this band model. But as we'll see, this rule can be broken very easily for many of the materials. So here's the rule. A crystal can be an insulator only if the number of valence electrons in a primitive cell of the crystal is an even integer. Okay? This means basically when you start filling up your energy levels, if you remember, for an what we do is we fill each state with each orbital, or if you like, with a spin up and spin down electron. And if you have this total number of electrons to be an odd number, then you will have one electron left unpaired. But if you have an even number, that will be paired and that state will be filled. So you will have no room for electrons to be added or removed from that top state. So, sorry, no room for electrons to be added. So, in a way, this rule stems from that fact. And if you look at the periodic table, you will see that in the case of alkali and noble metals, there is one electron per valence state. If you look at alkaline earth metals, they have 2 electrons per unit cell, but they're metals, so it breaks the rule. So there's another rule that actually we can explain within the framework of this single electron model. Now I'm gonna explain what that might be. Again, let me draw this pi over a 0 energy. Now I can have a band like this. Okay. Now, as you can see, there is a gap between this band, this energy band, these allowed states. There's a gap here, but let's try to fill the electrons into these energy states. So I can have something like this. Let's fill it up. Now, as I reach to this minimum point of this band, now I'll be able to put some electrons here as well. Okay? What I end up with is some available states here and plenty of available energy states there. So I haven't filled up this band completely. There are available, if you think about the Fermi sphere, there is still room for moving it from a place to another place because I haven't filled up all the available energy states. So this becomes metallic, although I have 2 valence. So if there are overlapping bands, which is possible if you solve the equations for many materials, you can see that you can end up with overlapping bands. There's a gap. I mean, this is a continuous band, this is a continuous band, and there's a gap. But the energy values here and here are degenerate. They can assume the same energy values for different momentum values. So I end up with half-filled bands, which translates into a conducting material. Finally, we can have materials like, for instance, diamond, or silicon, or germanium, and so on. You can find a lot of examples like this. They have 8 electrons in their valence. It's an even number. So what you end up with is something like this. This is again K, pi over A, 0, E. Now let me draw a different type of band. Okay. So in these cases, you fill up all these available states with the electrons. and there's no empty state here and no filled state on the next band. And what you have here is an insulator or semiconductor. What determines it being a semiconductor insulator? The size of the gap, yes. So the size of this EG determines whether we call it an insulator or a semiconductor. Typically, if this gap is greater than 3 electron volts, you can say that it's an insulator. If it is less than 3 electron volts, you can say that it's a semiconductor. But that definition can be altered with respect to the hype that you want to create. For instance, there's this material, vanadium dioxide, one of my favorite materials. The energy gap is 0.6 electron volts, and what happens is that at 65 degrees Celsius, the material is a semiconductor indeed, but it makes a very sudden phase transition. It becomes metal, and we call this metal insulator transition rather than metal semiconductor transition because an energy gap opens, but although it's much smaller than 3 electron volts, saying metal semiconductor transition is not, it doesn't sound as significant as metal insulator transition, so people refer to it as a metal. So the transition, this definition of insulator and semiconductor is rather vague. It's not, I mean, this is the generally accepted rule. Okay. All right, so any questions? This one? So now what you can have here, okay, let me explain perhaps this one as well. Now I think we can give a break. Perhaps I can explain, I have 6 minutes. Let's give a break and then I'll explain, okay? Okay, so I was going to explain you this one more time. Okay, then. Okay, exactly. So now let's see what determines. I mean, we sort of now at a stage to understand how this works, but now let's write down a more rigorous way to understand how the Fermi level affects a material being an insulator or metal. Now, for the case of a metal, now I'm not going to write it with respect to K, but I'm just going to draw a straight line representing the K0 value, okay? So let's say my Fermi level, and I'm looking at the top of the band, so let's say this dashed line represents the Fermi level, okay? And these are two band edges at K equals to 0. So I know that this band needs to be filled because my Fermi level is up there. And then there's an energy gap here. So this is a gap, it's forbidden state. And then I'll keep filling my electrons to these states as well. Okay? So what I'll end up with is, let's say the top of this band also resides here, so there's another gap beyond this. But now I have available energy states within the vicinity of these electrons at the edge of the band. So I can move, I can change the momentum values of these electrons so that I can move them from one point to another. They can gain velocity if you like. But for the electrons here, there is no such chance. I cannot change their K values because the next K value is already occupied. So to be able to make such a change, I need to be able to, I need to look at the electrons at the Fermi edge, that sphere's edge, if you like. Another case where we can have is this. My Fermi level lies here, which is perfectly possible because we don't impose any conditions on the Fermi level. It's just, it denotes a certain distribution. So I'm going to have all my electrons to fill up to this level, but since this is gap, nothing to fill, no states to fill, so there will be nothing here. So this is a metal, and this is an insulator. Okay, and again, what the distinction between an insulator and a semiconductor is defined by the size of that energy gap. Now, what happens at finite temperatures? What happens if I start increasing the temperature for this system? Now, I'm going to draw the distribution function sideways. Okay, so let me draw this baseline, and this is going to be Fe. So at 0 Kelvin up till the Fermi level, this is going to go like that. And again, I can do the same thing here. At 0 Kelvin, this is Fe, and this is 0 Kelvin. I'm going to have such a distribution, which is consistent. What happens at finite temperatures? This is going to start spreading out. Now, look carefully. There's not much to discuss here because even if this starts spreading out, there are already available energies. They'll spread out. Everyone is happy and safe. But here, interesting stuff will start happening. Probability of occupying this band, this edge of the band, will start decreasing, while this tail although I messed up with my drawings, this tail will start extending towards this empty band. So this means my electrons here will have a finite probability of being in this upper band, and there will be absence of electrons here. And actually, if you do the math, you'll see that number of electrons here will be equal to absence or number of absent electrons there. So in a way, temperature redistributes the electrons to these energy levels, and there's a finite probability of finding electrons in the upper band. Now, I have been holding myself, but let's label these bands. This is called the valence band, and this is called the conduction band, for a very good reason. Because once you can start transferring your electrons to this band, there are available momentum states. They'll be able to move from one point. They'll be able to gain momentum. Okay? And this valence band is all completely filled. It's valence. Okay? Now, it should become more clear why we roughly say 3 electrons for the EG. As you keep increasing this gap, this tail will exponentially decrease. So the smaller gap you have, at finite temperatures, the more probability you have for your electrons to be in the conduction band. So this sort of marks the distinction between an insulator and a semiconductor. For instance, if you consider a 1 electron volt energy gap, then at finite temperature there will be a lot of absence of electrons, a lot of electrons here. And you can compare this to a case where you have a 6 electron volt energy gap. No matter how much you increase the temperature, this tail of the probability will not be able to extend towards the conduction band. It will still be close to 0. So there will be not enough electrons to contribute to the conduction. Is it clear? I mean, this is the basis of basically this single electron band model. Okay, this is a model that we are looking at, and this is a very nice model, by the way, for those who are working on DFT. This is the point, this is the 0 point. I mean, this is where it all stems from. This idea that you can take a single electron and look at everything in terms of the single electron. Then you can start introducing interactions, impurities, and so on and so forth. Everything stems from this basic assumption. So if you got this right, if you got this straight, then you'll have easier time understanding the rest of the stuff, I believe. Any questions regarding this? Yes? No? No questions? Okay. Yes? Yes. Mm-hmm.
For example, some material that conductors. So
Mhm.
never cross the upper line for that material.
Well, the challenge here, now we will solve the equations and you will see that it's why it's not possible. Now, 6 electron volts is quite a large energy gap. So to be able to reach, you can actually simply do the math. 6 eV equals kBT. So for the Boltzmann equation, this is something like micro electron volts. Okay, it's 8.5 10 to the minus 5. So you can roughly say it's micro electron volts. So this temperature will be millions of degrees. So we are talking about, in terms of temperature, very large temperature. So if you look at any Fermi distribution, then it's not going to be millions of degrees, but it's going to be thousands of degrees till you start, the tail can extend towards there. But most materials will either lose their properties at those temperatures. So you'll never see insulators becoming metals by simply, or conductors by simply increasing the temperature. But you can do this easily for silicon. You can start from 0 Kelvin. Silicon is a very nice insulator. As you increase the temperature, of course, there are other effects. But what you'll see is there's this carrier freeze-out zone. So electrons are not available. And then you'll enter a regime where it will start conducting. And yeah, so this is a simple answer to your question. Any other questions? Okay, now, again, just as a reminder, now we are going into real discussion of semiconductors. And then from that point on, we'll be dealing with semiconducting materials, and we'll look at their junctions with other materials, and also we'll start focusing on the surfaces. So far we have been assuming that our materials is sufficiently large that we don't have to consider the edges of our materials. But if you think about it, when you go closer to the edges, the assumptions we make, for instance, we assume that we are living in a periodic potential, right? So when you get closer to the edge, you'll see that that periodicity will start disappearing. So your wave function at the edges will be significantly different than the wave function within the bulk of the material. So we'll start looking at what happens at the edges, and we'll see there are lots of interesting stuff going on. And this will be very useful for understanding the mesoscopic phenomena that we'll see in the coming lectures. So there are several things we can explain regarding the semiconductors. First of all, again, let's draw this K versus E. Again, let's stick to the first Brillouin zone. Okay, and you can have a band. It doesn't have to be like this, but let's have it this way. Okay. So if, again, this is the conduction band, this is the valence band. Okay, it's not necessarily zero value. I may have lots of different bands at lower energies. I can define my E equals to 0 level here. So don't mind the energy scale. But this is my conduction band. So my Fermi level, basically it's defined by this Fermi level, lies here. Okay. So if the minimum of the conduction band has the same K value with the maximum of the valence band, this is called, what's that? Yes, that's a direct gap semiconductor. Okay. And as we'll see, direct gap semiconductors are quite important for optoelectronics, because I haven't explained that, but we'll see that. There can be another way of these bands aligned. If you have, for instance, something like this, I'm just making it up. So there is a delta K difference between the extremum points of the conduction band and the valence band. So the energy gap is still defined as this separation, just like in this one. But now the extremum points are at different positions. So this is an indirect gap semiconductor. Can you name a few examples? For which one? So it's gallium arsenide. For indirect? Yes, silicon. Germanium. I don't know. You can find many examples. Indeed, let me write down a few of them. Gallium phosphate. Then here we can have gallium nitride. Then monolayer of tungsten diselenide, molybdenum disulfide, diselenide, but only in the monolayer, as we'll see. And here you can write the multi-layers of tungsten diselenide, sulfide, molybdenum diselenide, sulfide, and so on. So the list can go on. The names are not too important, actually. I think it's sufficient to know that silicon and germanium are indirect gap materials, just for general information. And gallium arsenide is a direct gap, again, just for general information, should be sufficient. What else? Now, let's see. Now let's look at the conduction properties of semiconductors. Yes, please.
Can you explain the difference between these two? For example, is there I read somewhere that it's difficult for silicon to be conducted. Semiconductor is more difficult than for electron.
No. It's actually not. Again, it all depends on, at finite temperatures, how that distribution is separated, and also the energy gap, because the filling will be done in this fashion. You will fill the valence band, and if your distribution is something like this, sorry, again, I messed up with the drawing, but then you'll have a few empty states here and a few filled states here. And this is technically not any different than this case, because what matters in this distribution is only the energy gap. Okay? And as we'll see in the conduction properties,
No physical difference.
there is a physical difference. There is actually a significant difference. But the difference is basically this. If you want to take one electron from the valence band and excite it to conduction band, either you have to supply this energy so that it can make a direct transition, but it may not be allowed all the time, by the way, or you need to supply this momentum difference so it needs to scatter from something so that it can first go to an intermediate state. Because of the scattering, it will gain an extra, it will create an intermediate energy state, and then it can make a transition, which is an extremely rare event. So for indirect gap semiconductors, it's not a good idea to use them in optoelectronic applications. That's why these materials are much better in optoelectronics, because all you have to do is supply this energy, the energy required to take one electron from here to here, or vice versa. When you have an electron that's going to relax back, it doesn't need that momentum difference to be supplied from the lattice or scattering events or any other mechanism. This is much more probable compared to this one. So mostly it's related to the optoelectronics. Now, when we look at the conduction properties of semiconducting materials, there are two major things that we have to look at. First, the intrinsic conduction. Again, now I'm going to look at the band edge only. So, again, this is my Fermi level. And now, I have electrons filled up here, and also I have some electrons in the conduction band. Okay, so I have absence of electrons, if you like, here. And there are electrons. So obviously this is at some temperature that's greater than 0 Kelvin, so that I could transfer electrons from here to here. And as you can see, and as I mentioned earlier, number of electrons are equal to the absence of electrons here, because in this material I have a certain amount of electrons, and I know that these electrons came from the valence band to the conduction band. So if I have n electrons in the conduction band, then I need to have n missing electrons here. Now let's apply an electric field to drive these electrons. What will happen is, under the influence of the electric field, let's say it's going from here to here, my electrons will start moving to the left. I think it's pretty straightforward for here. I have electrons, I apply the electric field, there are available states so they can move in a certain direction. Now what will happen here? Let's simplify this. Rather than n electrons, let's say I have one electron that's absent in the valence band, and that electron resides in the conduction band. Under the electric field, I'll see that this electron moves in this direction. But how about here? Electric field also applies to this case. And although I don't draw them, we have many electrons here. Now, as I apply the electric field, this electron will want to, actually all the electrons will want to move in this direction, but there are no available states to the left of them. But this guy is lucky. It can move here. There's an available state here. So if I move one frame forward, this is what will I see. So this absence of electron actually moves in the opposite direction. In the second frame, this electron is now the lucky guy. It will go here. So this absence of electron, in a way, behaves like a charged particle. And if you see, it actually behaves like a positively charged particle under the influence of the electric field. I apply the electric field, this absence of electron moves away from the electric field. So this guy has a name, and it plays a very significant role. It's called hole. Absence of electron. And as you can see, it carries a charge. It effectively has a mass. So it's like you're trying to move these electrons packed in here. So they have a mass, they have a charge, right? But rather than looking at the motion of each single electrons, you look at the absence of electrons and how it moves. And that motion, again, comes in with a charge. Of course, it has an opposite charge because it moves in the opposite direction compared to the real particles. And it will have a mass because under the influence of a force, external force, it moves at a certain finite velocity. It gains acceleration. So it just behaves like a particle. So the overall conduction of a semiconductor not only comes from the electrons in the conduction band, but also comes from the holes in the valence band. So if we are going to write down the expression, but that is a very important conclusion that we can draw from this whole band model. Now, for the intrinsic case, again, let's write this down. Number of conduction electrons are equal to number of holes in the valence band. And this expression, I'm just going to write it down, but it's not too difficult to derive this one. And here A is a constant that has a value of 21 electrons per cubic meter Kelvin meters. Okay, so let me see if I derive. No, I haven't. So basically, you end up with this equation using the density of states, and the exercise that we have done for a quantum box applies to here. You just focus on this Fermi level, around the Fermi level, and then you can end up with this expression. So, okay, and with the number of electrons we have, we can end up with such an expression. Resistivity of a semiconductor is something like this. Again, I'm not going to derive this. So this expression tells us that this is the electrical resistivity. This is some constant. So resistivity of a semiconductor depends on the temperature. And as you increase the temperature, resistivity decreases, because that's somewhat expected. The distribution will spread out even further, and you will get more and more electrons and more holes. So the overall expression for the resistivity will be something like this. And this is a significant result because, in a way, it tells you that if you measure resistivity versus temperature for a semiconductor, then you can reach the energy gap value. That's one way to do it. Of course, it's not a good way to measure the energy gap, because as you change the temperature, the energy gap also changes with temperature. This is, here we assume that it's temperature independent, but imagine you have lots of atoms, and this gap actually stems from the potential energies of these atoms, if you like. And as you change the temperature, they start wiggling around more and more. So the energy gap starts changing slightly. Indeed, for silicon, let me see if I have the expression. There's a significant change in the energy, and most of the energy gap values that we give here are at room temperature. Okay, but still, this is if you focus on a finite temp or small interval, this gives an accurate measurement of the energy gap. Okay. Any questions so far? Now, each of these. If you remember, I think in our first or second lecture, we defined mu, which was the mobility, and here this is the magnitude of the electric field. And this whole expression is the speed of the charge carrier. Okay? And this was a measure of how fast carriers can move under the effect of an electric field. Now, if you remember, again, from the Drude model, we have written something like this, E tau over m, okay? And this was from the Drude model, just as a reminder. Now, for semiconductors, we can write down an expression for the conductivity. Now we know that the electrons will contribute to the conductivity. So this is one expression that I can write down. This is the mobility of electrons, density of electrons, and electronic charge. And then we also know that holes will also contribute to the mobility. So I can write down a second expression for the conductivity. So my total conductivity comes from electrons and holes. So I'm assuming basically when I focus on the edge of these bands, I can approximate that these electrons sort of behave like free particles. So I go back to my Drude model to write down such an expression. And it turns out this is not a bad assumption after all, and it fits quite well with the observed values. There's one other thing that I would like to explain, which is called the effective mass. That's my phone. Now, what is effective mass? This term is basically, I mean, if you take the electron's free mass and do a full quantum mechanical treatment of these semiconducting materials, that's fine. But this is something that we cannot do. We are after a simple picture, so we are trying to remove many parts as possible. So what we do is, rather than dealing with the free electron mass and lots of terms that can affect the electron's motion, let's modify this mass, define an effective mass that captures all the interactions, all the scatterings and other events into that effective mass term. So define a new mass, so I can still apply these models and these expressions to my electrons. And indeed, this turns out that it's not a bad approximation. If you think about the mass of an electron near the valence band and the conduction band, this is the expression that you will see. 1 over m star equals to 1 over h bar squared and second derivative of energy with respect to momentum. So in a way, you're looking at, the first derivative would be the slope of this guy here, and the second derivative gives you the curvature. So how fine this thing is curved defines the effective mass of electrons. So it's like, you can take it as, I like giving this analogy. Let's say we have a tank of water, okay? And then there's a guy inside this water, and he tries to move within this body of liquid. Now, how would you solve, let's say there's a certain force pulling him, or that you can say that as well, and even if there's a force and he has a certain mass m, he will reach to a drift velocity, right? Because there's an opposing force. As he accelerates, as he gains velocity, the hydrodynamic forces acting on this guy will basically oppose this force. So he's going to gain a certain velocity. So to be able to solve this problem, you have to calculate all the hydrodynamic forces acting on this very strange surface, right? It's a very difficult problem to solve. Rather, you can do is, rather than taking his actual mass, you say he has a modified mass. So that force will only bring him to a certain velocity or give him a certain acceleration. So rather than dealing with the force that it pulls it and the forces because of the water, now I reduce my problem to this force only plus the modified mass of this guy, okay? So is this analogy clear, or it may confuse you more? So think about it. I mean, you're trying to move in the air. In air, the air is also exerting a force on me, but it's not significant. Now fill this room with water and try to move here. Now the force that tries to pull me has to pull me plus the hydrodynamic forces that are acting on me. So there is a modified mass term. Here the case is extremely similar. I'm looking and I'm focusing on the electrons that are at the edge of this conduction band and the valence band. And what I do is, rather than saying, let me take the free mass of the electrons and use all the forces and all the potentials that are acting on the electron, I say, well, let me define an effective mass and use that mass in my calculations. So it turns out this is a very valid approach, and this effective mass needs to be done for both electrons and holes. Because, I mean, this turned out to be a nice example. If you have a very sharp edge of your energy band like this, then this means that the effective mass you're going to have is going to be small. If you have a very broad edge of your band, then the weight of your electrons is going to be actually very high. Okay? So, sorry, effective mass, not weight, is going to be very high. So you can use these effective mass terms in the Drude model to figure out the mobilities. And again, we can find an expression for tau based on our measurements. So this expression, these expressions, still valid to a certain extent in our semiconducting materials. Any questions? Mm-hmm.
Aren't equal to each other?
They're equal to each other, yes.
And the mu of E and mu of
Mm-hmm.
difference?
They can be different. If you look at this, I mean, it completely depends on how the valence band and conduction band edges are curved. You can have a completely symmetric case, like I've drawn here. You can have a completely asymmetric case, very flat base of the conduction band and very sharp tip of the valence band. So you can end up with different effective masses. Thus, you can end up with different mobilities for holes and electrons. And indeed, let me write down a few values for electron and hole mobilities. In the case of indium arsenide, for instance, electron mobility is like 30,000, while the hole mobility is 450 square centimeters divided by volt seconds. In the case of silicon, this value is 1350 and 480 for graphene, of course, this is at low temperatures on silicon dioxide. You have completely symmetric bands, and you have same mobility values for electrons and holes. Okay.
And the mass
Mm-hmm.
for both of them we consider equal for holes and
For graphene, are you talking about?
the
No.
mass of holes and
No, it's most likely very different. Okay, so I mean, actually, if you look at silicon, for instance, there is no single valence band. There are multiple bands. They're called light hole bands, heavy hole bands, and then there is spin orbit splitting. So the whole spin interacts with the orbital momentum, angular momentum. So there is another band form. So in real case, it rarely is equal to each other. So mass of electrons is significantly different than mass of holes. And you don't have a single mass for holes. You may have multiple masses for holes in the valence band. Okay, so in reality it's more complex, but even for our case, you can safely assume that masses for holes and electrons are different. The exception, for instance, here is graphene, because it has a completely symmetric energy diagram. It's basically at the edge of this. So this is your Fermi level. Then you look at this K point at the edge, near the Fermi level. It's completely symmetric. So these levels filled up till here, okay? And any electron you excite from here will end up here, okay? So you have a completely symmetric case where if you look at the slope or the curvature of these, they have the exact same value. So you end up with the same mobilities because you have the same effective masses. Any other questions? Yes? Well, I didn't drive it. The expression is this. So this is volt per centimeters. You can say this is centimeters per second. And I mean, it turns out, rather than using meters, this is a more convenient way to express the mobilities, because for most common materials, if you use meters, they'll become absurdly small numbers. So this is how you write it down. Well, if you don't have any other questions, we can finish this lecture today. There will be no class on Friday, okay? But we'll make it up next week. We'll start early at 8:40 to make up for the missing hour this week. And next week we will start with, I'll introduce a few more concepts regarding the semiconductors, and then we'll start looking at surfaces of semiconductors. We'll start bringing semiconductors together, and then from that point on we'll have the basics finished, and then we'll start looking at electronic transport in solids. So how electron moves from one point to another, and also we'll start looking at some interesting phenomena like how electrons localize around defects and so on, which will form the basis of mesoscopic phenomena that we'll see. So from next week on, we'll be going into probably newer concepts to some of you guys, okay? All right, see you on Tuesday next week.